So here's a little help on this implicit differentiation stuff we just got started on. What happens is that sometimes functions aren't written in forms that are really conducive, well, to taking derivatives in a manner that we've done so far. Sometimes you have functions that are, y is not by itself. We don't have y all alone, or whatever variable we have. It could be s, any type of variable. So let's just take a function. Usually we like taking derivatives of things that say y equals. What we'll talk about a little bit later in this short video is that we'll call that the explicit form, like a plain, straight up, explicit, easy to understand function is written, y equals. Well, when it's not explicit, the form is what we call actually the implicit form of a function, like this one. So 7x squared minus y equals 6x. What I have is, I could solve for y, but what I have is the function y equals is kind of implied in here if I did a little work to get there. So that's the generation of the word implicit differentiation. It's taking the derivative of, well, usually functions where we just usually can't get y by itself. It's not efficient, wouldn't be useful, or we're dealing with a lot of other variables at the same time. So anyhow, I'm going to just show you this straight up. If you have to deal with this, and I say solve or do implicit differentiation, what you want to do is take the derivative like you always would. And so if you could take a look at this, I just took the derivative. Like you know the power rule, take the power out front, multiply it by the whatever coefficient there is there, so that's where the 14 comes from. Now x is to the first. Take even y, just treat it like it was an x. Take the derivative of that, you should get 1. And the 6x, take the derivative of 6x, you should get 6. That's great. You're only missing one thing when I say take derivative implicitly. It's that when you took the derivative of y, you can't write just the 1. You have to add in this dy dx afterward, this thing called a differential. And what it is your statement that I just took the derivative of a y with respect to x in that function. So after that 1, I should have dy dx. That's it. That's the only other thing about implicit differentiation. It's go through, take the derivative as is, but anytime you take the derivative of a letter that is not, in this case, dx, not the variable that you see down here in the bottom, we have to put d variable, in this case dy, over dx after that variable. So here's the next piece, solve for dy dx. So that means subtract 14x, that means divide by -1. And that means when you divide by -1, you can make the signs change on each of those or just turn the whole thing around. Either one's fine. There you go. There's our derivative, dy dx. Well, that's doing it implicitly. Let me go back and show you that if I wrote the explicit form of this equation, by the way, this is number 6 on WebAssign, should look a lot like yours, so you can probably duplicate this. If I solve for y from the get-go, the derivative is really easy. Here's y equals 7x squared minus 6x. Believe it or not, that's the same as the function in the problem, or I just rewrote it, solve for y. You can trust me on my algebra there. Take the derivative, 14x minus 6. Interestingly enough, isn't that the same thing we just got implicitly? Well, if you can solve for y in a function, the implicit derivative will always be the same as if you solve for y explicitly and then take the derivative. It'll always work out the same. Implicitly can just be very efficient. You don't have to solve first. You can solve later when you get dy dx by itself. Let's talk a little bit more about that. Again, here's the explicit form. Then the implicit form is when I go back to my original. Let me delete all that stuff. Implicit is when y is not isolated. And what happens is, interestingly enough, explicit, think of it in terms of not like, throwing out some explicative type of thing. It means, give it to people straight. That's what really the explicit lyric kind of idea comes from, is that you're just giving it straight, not beating around the bush, the function straight up. Well, implicit causes us usually to be somewhat explicit. Those of us who are taking this on for the first time, it's complicated. But now you've got the idea that it's just adds one little step to your derivative, that d variable dx, or we'll expand our variable horizons here soon, but it shouldn't be too bad. So important to note that this differential notation can be confusing. So what it means is d dx that you see here is the action of taking a derivative. If I do it of y, it would be dy dx. If I do it of w, it would be dw dx. If I take the derivative d dx of, I don't know, somebody's name, Alfonso, it would be d Alfonso over dx. It's the action of taking the derivative. If you do it of x, d dx of x would be dx dx. And interestingly enough, that ends up being 1. So actually, that's actually why we don't see an implicit. That's why you could technically go back in each of these and write, after each x term, you could write a dx. The ones I took the derivative of where there's an x, I could write dx afterward, but that cancels to 1, so we ignore it. So that's the end of the story on implicit differentiation. If that last part was too much information, just to go back to how I did it from the beginning, really it's take the derivative like you always have, d variable if it's not an x over dx, so the dy dx in our case had to be entered in there, solve for dy dx and move on. Email with questions.